Hey or not Chem Kids. Hey Phys Kids, Mr. C here. Gosh, I don't know why I said Chem Kids. But today we're going to talk about torque and static equilibrium, or sort of just a brief introduction to what torque and static equilibrium are. So before we get to static equilibrium, we first have to sort of understand what torque is. And torque is just the force that causes rotational motion. It's always going to be about an axis. The big example for you would be whenever you like push open a door. Whenever you push a door, you apply a force on a door. It causes the door to rotate on its axis, and in this case, the axis is going to be the hinges of the door. But anything that you apply a force to and it causes some sort of rotation, provides a torque. So if you're using a wrench or a screwdriver, you're turning on a faucet or anything like that, or you're even turning your steering wheel of the car, you're applying some force that is causing rotation, and we call that rotational motion torque. Well, I guess the force that provides that rotational motion is torque. Torque is going to depend on three different factors. And the first factor is the magnitude of the force that we apply. So the bigger the force, the more torque we're going to have. And that can be seen, the harder you push on a door, the faster that door opens. So it's going to be proportional to the force applied. It's also going to be proportional to the direction of the force applied. Whenever we apply a force that is perpendicular to our radial line, so like in the case of F1, we're going to have the maximum amount of torque possible because only the perpendicular portion of the torque is going to produce that torque or this motion in that case. So anytime we have a force that's applied parallel to the radial line, we're going to produce no torque at all. So like F3 here is producing no torque. In the case of F1, because it's completely perpendicular to our radial line, the entire force produces torque. And in the case of F2, only the Y component here is going to produce torque. So only the portion perpendicular to our radial line produces torque. The portion parallel produces no torque at all. And then finally, it depends on the location of the applied force. So how far are we from our pivot point? So from the point where we're pivoting to our force, and it's going to be directly proportional as well. So the further away we are, the more torque we can produce, and you can see that with the door. If you push a door all the way at the handle, you can open that door very fastly, very easily. But if you apply that same force pretty much right near the hinges of the door, it's going to be very, very hard to open that door. And then if we apply a force at that sort of pivot point, we actually produce no torque at all, which is kind of crazy to think about. So the further away we are from our pivot point, the more torque we can produce. When we combine all of this into an equation, we find out that our torque, which is tau, is going to be Fr times the sine of phi. And this phi here, that angle, is just the angle between the force and the radial line. Another way that you can look at it that I think is sometimes a little more sort of insight of torque, if you just want to write it as a T, that's fine, but it's going to be the perpendicular portion of the force times the radius. So sometimes I like to look at it like this. So it's a perpendicular component of your force times the radius. And if you ever have the angle where it's not the angle between the vector and the radial line, you won't be using sine, you'll be using cosine. So I always like to look at it as the perpendicular portion of the force times the radius. And the units of torque, because units are super important, are going to be a Newton times a meter, and torque is a vector, so it does have a direction. So make sure to keep that in mind as well. So in this case, the torque done by this wrench is going to be the perpendicular portion of our force, which in this case is all of the forces. The whole force is perpendicular to our radial line here, times our distance of 6 centimeters. We plug that all into our torque equation, and we find that we have a torque of 2.4 Newton meters in this case. And the way that we measure direction is either clockwise or counterclockwise. And in this case, our torque would be a clockwise torque. As we can see, as we apply that force down, our wrench is going to move in a clockwise motion. Not too hard. Whenever we have, like I said, that force at the angle, you want to make sure that it's the perpendicular component of the force. the one that's opposite of your angle. You want to make sure it's that y component or whatever component is perpendicular to your radial line. So like in this case, we want that Fy component. If it's not, like I said, you have to use cosine. Like if maybe you have that angle instead for some reason, you'd want to use cosine instead of sine. But you always want the perpendicular portion of the force to your radial line whenever you calculate out a torque. So let's look at this example here. Now we have an 80 Newton force that acts on at the end of a 12 centimeter wrench as shown in the picture. Find the torque. Well, this here's our radial line, and our force right here is at 80 newtons. We can see that if we remember back, we know that torque is going to be equal to the perpendicular portion of our force times our radius. In this case, the perpendicular portion of our force is right here, and we can get that using the sine of the angle because it is opposite of our angle. So in this case, our torque will be equal to our force times the sine of our angle times our radius, or 80 newtons, times the sine of 60 times 0.12 meters, and that will get us what our torque is. In this case, it would be 8.31 Newton meters. The next thing I want to talk about is static equilibrium. And static equilibrium, we say the way we define static equilibrium in physics is whenever we said there is no net force acting on our object and there is no net torque. So both the net force is equal to 0 and our net torque is going to be equal to 0. And this is where direction is going to kind of come in handy. So that first condition, we look here, we really have two because we have to break up forces into x and y. So our F net x is equal to 0 and our F net y is equal to 0. And then our second condition says our net torque is equal to 0. Statics are really used whenever we design bridges a lot. Like whenever they design the Golden Gate Bridge, they have to make sure that the torque is equal to 0 and the forces are equal to 0. Because sometimes your forces may be equal to 0, but you would have some net torque. And if that were the case, like in the case of the Golden Gate Bridge, your bridge would actually start rotating around some axis of rotation, and that would not be good. No one wants to be driving on a bridge while it starts rotating. So static equilibrium is very important, especially for engineers, because they have to make sure the forces are balanced and those torques are balanced. Whenever you solve static equilibrium problems, the first thing you want to do is draw a free body diagram so you can identify all the forces, because the forces will help you determine what your net force is, but the forces also help determine what your torque is, because remember, the torque is dependent on all of the forces acting on our object. We're going to want to choose some axis of rotation and a pivot point. And the pivot point is where the least amount of information is given or the most sort of unknown. So you can pick this wherever you want to pick it really, but usually it's going to be at some fulcrum. If we're doing some sort of like seesaw problem, it'll be at the center of the fulcrum, or a lot of times it'll be obvious where that pivot point is going to be, or we'll tell you where it's going to be, but sometimes you have to choose it. You just want to choose it where you know the least amount of information. That way any forces acting at that point produce 0 torque. And then you want to do the sum of your torques about a chosen axis or pivot. So just remember the sum of all your torques is going to be equal to 0. Note about direction, I did mention that it was a vector and we measured it as counterclockwise and clockwise. We say any torque that is moving or causing a counterclockwise rotation is going to be positive, and any torque providing a clockwise rotation is going to be negative. So anytime you're going counterclockwise, we're positive. Anytime you're going clockwise, you're going to be negative whenever it comes to torque. So make sure you keep that in mind whenever you do the sum of the torques, because direction does matter. And then also you want to check the sum of your forces are equal to 0 as well. So you want to check that in both the y direction and the x direction, because once again, force is a vector. And then last, you just solve for whatever you don't know. If you're looking for a force, you solve for force. If you're looking for a torque, you solve for torque. But you want to solve for whatever you don't know. So here we have an example problem. We have a 3 kilogram mass is hung on a 200 gram uniform meter stick 20 centimeters from the center. A 2 kilogram mass is hung at a distance that balances the stick when placed on a fulcrum at the center. Find the force exerted by the fulcrum on the stick and find the distance that the 2 kilogram mass is from the fulcrum itself. So the first thing we want to do is we want to draw that free body diagram and label all of our forces. So whenever we do this, we have 4 forces acting on it. We have our force of gravity from our 3 kilogram force that's hanging, our force of gravity from the 2 kilogram force. We have the normal force that's being exerted by the fulcrum, and we have the force of gravity from the meter stick, in this case, being pulled down by gravity. So in this case, our first part of the problem, we want to figure out what the force on the fulcrum is by the stick. So we're going to use that first condition of static equilibrium, because this is in static equilibrium, it's not moving. But we want to say that our F net in the y direction, in this case, because all of our forces are in the y direction, is equal to 0. And so if we look at this, 0 has to be equal to, well, the normal force is going to be positive, minus the force of gravity of the meter stick, minus the force of gravity of mass 3 kilogram, and minus the force of gravity of that 2 kilogram mass, or our normal force will be equal to the force of gravity of the meter stick plus the force of gravity of mass 3 plus the force of gravity of mass 2. And if finally we can sort of plug in our variables, so it's the mass of the meter stick times gravity plus mass of the 3 kilogram times gravity plus mass of the 2 kilogram times gravity. And I always like to factor out my gravity if I can. So it'd be the mass of the meter stick plus mass 3 plus mass 2. And this would be what the normal force of the fulcrum exerting on the the normal force of the fulcrum on our meter stick here. So our next part is we want to find the distance the 2 kilogram mass is from the center of the fulcrum. So we want to know what this distance x2 is here. And we're actually going to want to use our torque in this case. So if we go back and we have all of our forces, we're going to use torque. So we know that our net torque has to be equal to 0. And in this case, our net torque is going to be equal to the torque from Fn plus the torque from the FG of the meter stick plus the torque from the mass 3 plus the torque from mass 2, or the 2 kilogram mass. But when we look at this, we see that our normal force and our force of gravity are both acting at the pivot point, because we're choosing this point here as our pivot point. In this case, we don't know anything about that information. That's where we're measuring all of our radiuses from. So we're going to choose that as our pivot point. And because the normal force and the force of gravity are acting at the pivot point, we can go ahead and say that they produce 0 torque. So really, our two net torques are just going to be the torque from the 3 kilogram mass plus the torque from the 2 kilogram mass. And if we look at signs here, the 2 kilogram mass is providing a clockwise rotation, so it's going to be negative. And the torque from the 3 kilogram mass is producing a counterclockwise rotation, so it's actually going to be positive. So I can go ahead and say that 0 is going to be equal to the torque of the 3 kilogram minus the torque of the 2 kilogram, or the torque of the 2 kilogram has to equal torque of our 3 kilogram mass. We know that torque is going to be equal to the perpendicular component of our force times the radius. So to be F2 perpendicular times the radius is equal to F3 perpendicular times its radius. If we look at both of these forces, though, they're both, if we look at our axis of rotation, which goes along the meter stick itself, the entire force from 3 kilogram mass is going to be perpendicular, and the entire force from the 2 kilogram mass is also perpendicular. So in this case, the entire force goes into producing that torque. So we can just go ahead and say it's F2 times R2 is equal to F3 times R3. We want to know what that radius 2 is, or this x2 here. So R2 is going to be equal to F3 times R3, all divided by F2, or mgr3 over m2g. G cancels out, and we're left with our distance is going to be the 3 kilogram mass divided by the 2 kilogram mass times the radius, or the distance, of our 3 kilogram mass. So that is how that problem is solved. Make sure you stick around. I'm going to have a quick question that I want you to answer in this video. 4 points. because we're doing points to make sure that you watch the video. So make sure that you answered all the little questions in this video that pop up on your screen, and I will see you in class to talk more about torques and static equilibrium.